designing, manufacturing, installing, and maintaining the high-speed electronic computer, the largest and most complex computers ever built.
Hello. Welcome to another episode of Building Better Systems, the podcast where we explore tools and approaches to make our software more correct and secure. Today we're doing an episode that's a little different. We're exploring a more timely topic. We're exploring a paper that recently came out in the homomorphic encryption space called On the Security of Homomorphic Encryption on Approximate Numbers. The paper is by Bayu Li and Daniele Miciano. So joining us to discuss this new paper today is Alex Malozemoff, a principal researcher at Galois, focusing mostly on secure computation. Thanks for joining us today, Alex.
Thanks for having me.
So today we're going to talk about the recent new attack on the CKKS homomorphic encryption scheme. But before we dive into the details of the attack, can we talk a bit about what homomorphic encryption is?
Sure. So homomorphic encryption is a form of encryption which allows one to compute over the ciphertexts. So with normal encryption, you encrypt a message, and then you can decrypt the message and get back that same message. With homomorphic encryption, you can encrypt a message and then compute, in theory, whatever you want on that encrypted message, and then decrypt the results and get back what would have been the computation on the original message.
And when you say compute, it means you can manipulate it, you can learn things about it without learning things about it. You can get statistically relevant information out of a set of those messages. What does computing on data that's encrypted mean?
So in theory, it means you can do any type of computation that you would do, like written as a C program, say. More formally, you can view computation as what's called an arithmetic circuit, which is basically additions and multiplications. So you can do any sequence of addition and multiplications on one or more ciphertexts.
Why would you want to do that as opposed to encrypting something, transporting it, or storing it in encrypted mode, and then when you need to either manipulate, compute on it, decrypt it? Why would you go for something like homomorphic encryption?
Sure. So the advantage here is you are never revealing either the input or intermediate values in the clear. So a potential use case for this is I'm a company and I want to do heavyweight analysis. I don't have necessarily the resources for it, so I want to do that all in the cloud. But I don't trust the cloud provider with my data. So in theory, if homomorphic encryption reached a point where it was sufficiently performant, I could encrypt my data, send it to the cloud provider. The cloud provider can then do the computation I tell it to do on that data, get a resulting ciphertext, send me back the ciphertext, I can decrypt it and see the result. And now the cloud provider never sees any of my data in the clear. That's kind of like the one of the most compelling use cases for homomorphic encryption.
So that sounds incredibly promising, and there's a number of groups implementing libraries of homomorphic encryption primitives, right?
Yeah. So I would say over the last, let's say 10 years, I guess homomorphic encryption has only really been around since I think 2008. But in the last, say, 10 years, there's been a huge number of libraries, or a huge number of schemes and performance improvements to these schemes and libraries, as well as various startups and major companies pushing homomorphic encryption. So it's definitely a rapidly growing space in the crypto world.
And CKKS, which we're here to talk about today, is a scheme. So it's not any specific implementation, but it's a way of doing computations to accomplish homomorphic encryption.
Correct. It is a particular form of homomorphic encryption that has certain properties, which I assume we'll get into. I think it was published in 2017, so it's fairly recent. but due to various performance characteristics it has seen widespread adoption throughout the community. There is an ongoing standardization effort in homomorphic encryption, and CKKS is one of the important schemes that is trying to be standardized. So it's definitely a very important homomorphic encryption scheme.
And so the paper that we're here to talk about, if I understand this correctly, these researchers have found essentially avenues of attack or break this scheme, and a number of open source libraries that implement this scheme. Is that right?
Correct. So they have a theoretical attack on the scheme. So on the kind of pen and paper description of homomorphic encryption scheme. And they demonstrate its practicality by taking, I think, 3 or 4 open source homomorphic encryption libraries that implement this scheme and demonstrating that the attack works. So they both show that the attack is theoretical attack on the scheme and is practical to implement and deploy.
And has this attack fully rendered the scheme useless, or has it limited the situations under which it's safe to use the scheme?
So I think it's fairly subtle, but I would lean towards the latter, although you would have to make assumptions that I would argue you shouldn't be making. So the attack in particular depends on the adversary seeing the decrypted result. So the adversary is allowed to encrypt whatever they want, which normally in homomorphic encryption you can. It's a public key encryption scheme, so anyone can encrypt something if they have the public key. But only the secret key holder can decrypt. This particular attack relies on the attacker being able to see the decrypted results. So at a first glance, it seems, okay, maybe this isn't too realistic, because why would the results be available to the attacker? But you can imagine many scenarios in which this would be the case if the results are part of public research, and so those results are published somewhere. Any type of scenario where the results of the computation are made public could potentially be an avenue to launch this attack.
So if you're going to use this scheme, you would need to be very certain that this was not going to be a problem. So it's really raised the bar for the guarantees you need to have in order to apply it.
Yeah, exactly. It's no longer a cryptographic guarantee on the scheme that you can rely on and deploy in any scenario you want. You would have to have some other measures to control the disclosure of the decrypted values. And generally, that's not a very satisfying kind of cryptographic guarantee.
So even at a performance cost, it might end up being preferable to pick something that gives you less risk at the end of the day.
Yes. So the paper presents, I believe, some heuristic approaches to addressing this attack. There is no cryptographically secure approach to address this attack, but you can address it heuristically, at least for now, at a cost of performance. So there's a bit of a trade-off.
What do I need to be doing or who cares? who should care about this, especially from the people who might be listening, and why?
So I think there's various people that can care. Definitely if you are looking at using homomorphic encryption, in particular CKKS scheme, it's worth being aware of this attack. And if you are deploying CKKS, seeing at least initially whether the required parameters of the attack are relevant for your deployment scenario. I think more generally, it's an interesting case study in the mismatch between security definitions and the intuitive guarantee you'd want out of a crypto scheme. So any crypto scheme that's proved against a security definition is proved against that particular definition. But that does not mean there couldn't be an attack that is not captured by that definition that is still a realistic attack. And this is an example of that, because the CKKS scheme is proven secure under what's called INCPA, which is indistinguishable against chosen plaintext attack. It's a very common security notion for encryption. And the scheme is secure in this setting. But because of the way CKKS works, it's a so-called approximate scheme. So it doesn't work. You don't, when you decrypt, get the exact result of the computation. You get an approximation of the result on the computation. And so there's some error added to the result of the computation. And that error is a function of the secret key. And so if you can see the results of the decrypted value, you're seeing some error term, which is a function of the secret key. And if you have enough of these, you can learn the secret key. So in terms of your standard, in terms of your standard encryption notion, the scheme is fine, but there is a intuitively reasonable attack outside of the security notion that the notion doesn't capture. And it's important to keep this in mind when thinking about the guarantees of a crypto system, because it's always secure to a particular definition. And so you can't just see a proof, or you can't see the claim that a scheme is provably secure and necessarily be fine with it. It's provably secure against a particular definition, and it's important to also understand that definition and what the definition is claiming.
So in one sense, this can feel like a bit of a blow to the homomorphic encryption community, since people were starting to use this particular scheme more often. But in another sense, I think there's a really optimistic view where part of why the cryptography community is so strong is this constant reevaluation of everything that people start to centralize around. And this is why we see NIST being so eager, for example, to standardize around post-quantum, is to really put the bullseye on someone's back. And every time we get a reminder of what you just mentioned, this idea that a proof isn't enough, you need to really evaluate what the proof is saying in the context that it's being used. I think every time researchers see that, it serves as an additional reminder. We've got to be careful about this. Let's think about now everybody that's using this kind of proof of this kind of scheme and evaluate them one by one. Yeah. So it definitely is overall to the benefit of this community that this kind of thing is going on.
Yeah, and this happens regularly. I mentioned this INCPA notion, indistinguishable against chosen plaintext attack. That for a while was the standard notion for encryption. And then people realized, well, it's actually not secure if the adversary is able to feed ciphertext to, say, the decryption procedure. And so they came up with INCCA, indistinguishable against chosen ciphertext attack, which is stronger than the INCPA notion. And something very similar is happening here, where for this particular scheme, because the output of the decryption is an approximation of the correct value, the chosen plaintext attack notion is insufficient. And these definitional issues come up every once in a while in the crypto world, and yeah, it definitely points to this ongoing hardening of the security claims.
It's definitely seeing the glass half full.
Yeah. So this paper just came out recently, so there's still hope that this new security notion that the authors propose can be achieved and can be achieved relatively efficiently. So I wouldn't rule out the possibility that a variant of CKKS with similar performance could be made secure against a stronger notion and thus be resistant to these style of attacks. So it's still early. I think it's too early to rule out that, don't use CKKS because of this attack. I'd be cautious of using it with the heuristics due to the reasons I mentioned. You really would have to have a good understanding of what you'll be doing with the outputs. But I wouldn't rule out CKKS for good because there's still potential that someone could patch this attack in a cryptographically secure way.
So this is the first time I ever heard of CKKS, and I've been around the term homomorphic encryption for a few years now. If some of these things are ironed out, who and in what ways do you think this scheme will be used? I know the paper mentioned, in addition to the open source libraries, mentioned machine learning on encrypted data. Is that something that this is promising for? Why and why not? What are the others?
Yeah, so that's the main application of CKKS. And the benefit there is machine learning as is approximate. There's error in your machine learning model. And so why worry about getting a completely accurate result using another homomorphic encryption scheme when there's already error in the model? What if we could make things much more efficient and add a little bit of homomorphic encryption error? And that's basically the ideal use case for CKKS, where the computation itself already introduces error. So sure, you're adding maybe a little bit more or a different type of error using CKKS, but you gain a lot in efficiency.
What would that mean for ML, algorithms and schemes? Does it mean that you can essentially feed a machine learning algorithm, or call it whatever, encrypted data without you ever seeing it, and then you get kind of a prediction engine or whatever that is out the other end?
Yeah, so a classic example is like neural networks. You could imagine encrypting the weights of your neural network so that you can evaluate the neural network on some input, on some encrypted input. And that could allow someone to deploy an homomorphic encryption model of a neural net on the cloud and then feed it data without worrying about leaking the neural net to the cloud.
That's amazing. Well, that was very informative. Thanks for taking the time to talk to us. We'll see you next time. This was a little bit of a different episode of Building Better Systems. And see you all later.
Yeah, thanks again for having me. This was fun.